So theorem 2, Glibenko-Cantelli. So Glibenko-Cantelli. Okay, theorem 2. And what we have for this theorem is that for any distribution function or cumulative distribution function, then we have that the empirical distribution function will converge to the actual CDF, and this wouldn't be surprising, right? Because this is, we're looking at an average of indicators. Indicators are bounded, so therefore, the expectation would be bounded, and of each of the elements, of the sum, and therefore, you have the law of large numbers telling you that they will, it will converge for every t. Now, what Glibenko-Cantelli tells us is more than that, because it talks about uniformity over all of the possible t's, right? And so we have convergence almost surely, and this is of course under the product measure. Yeah. Okay, and you would think that we have a sequence of CDFs and then converge into a CDF. So one would think, well, this really resonates with lemma 2 from the last lecture. But of course, we have randomness in this sequence here, yeah. So we cannot just directly apply that, but we can apply a result that we've seen, yeah, to show this. Okay, so let's write proof then. So in the proof, we're going to assume, and this is not necessary, but certainly for this type of, well, for the proof that we are using, that we are introducing now. So we're going to assume that f is continuous. Yeah? Okay, so if it is continuous, then let me note, actually this doesn't need the continuity, but let's note that, this difference, we can write it simply as 1 over n and the sum from 1 to n of the indicators minus, this is I guess, so minus the expectation of the indicator for some x1 if you like, anyway. And so really this has the form of, a theorem that we've seen already, or maybe a result that we've seen already, which is proposition 2, yeah, from section 2. So this is the uniform law of Lattice numbers. Okay, so we note this, and so we can use, the uniform law of large numbers, and this is, as I was just saying, proposition 2, okay. And so what is the family of functions that we are sort of taking the supremum with respect to? Well, this is just simply, this calligraphic H given by the indicators, of course, right? Okay, so minus infinity, t, and this is for t in R, okay? Okay, so now what we need to do, therefore, is to cover this calligraphic H with our brackets, okay? So to cover this calligraphic H with brackets, okay? So we're going to note that for all epsilon, so remember we need to make a statement that is valid for all epsilon. So for all epsilon, and let me assume, that the inverse is in the natural numbers, and this is without loss of generality. Okay, so we don't need to assume this, but just for simplicity. So we're going to note that we can define. So we can define Ti to be the counter image of I epsilon, for I going from 1 to n epsilon minus 1, okay? And let me define, okay. I didn't define the, okay, so here we just write n epsilon equal to precisely this epsilon to the minus 1, okay? Actually, maybe it's a bit cleaner if I just write, okay, so I just write this here. Okay, so we can define this for all of these guys, and then, and I mean these TIs are going to be different, right? And that's thanks to this continuity. Okay. So then, what can we say? Well, letting t naught be minus infinity and t n epsilon be infinity, together with sort of the, I guess, the agreement that this is going to be exactly 0 everywhere, and also that this guy is going to be 1 everywhere. Then by this continuity of f, so by continuity of f, we get that precisely the difference in expectations, these guys, of a ti minus infinity ti minus 1, okay? So this guy, so the difference is going to be simply, fti minus fti minus 1, and this is simply going to be epsilon. Yeah? And so the family, so this family of brackets, so ti minus 1 in this case, and then the ti. Now I goes from 1 to an epsilon. So this family is precisely the set of brackets to justify the proposition. Okay, so of course I'm skipping a few details, and you should check this. Yeah. So you should go back to this proposition 2.2. Okay. Proposition 2.2. So this proposition 2.2. Okay, and check things. Yeah. And so, but this is rather to justify not the proposition, but the theorem, yeah? So you use the proposition to justify the theorem, yeah? Theorem. Okay. And we would be done here. Okay, so this is this is regarding a law of large numbers for this capital F, but, can we say more like a central limit theorem? Well, it turns out we can. So furthermore, a uniform central limit theorem justifies the following result. Yeah? Okay, so what is this? Well, this is what it's called, by the way. So this is called Donska's theorem, what is common, but let me write a few names because they all contributed one way or another to it. So this is Doob and Donska at different times, by the way, so none of them was sort of collaborating. Yeah? Skorohod and Dudley. Okay, so I will go into details of the history in a second. So this is Skorohod, Dudley, Donska, and Doob. Okay, so what we have? Well, we have that as n goes to infinity, we get that the fn minus f. When rescaled by the square root of n, well, if we were looking at a pointwise limit, then we would expect, central limit theorem, so that would be fine. But now we will see something that is in a slightly different fashion. Yeah, so I'll comment on the meaning of the left-hand side here. But this is, just trust me that this goes to something that we call this GF, and I will talk now in a sec about, all of this. And in what sense does this happen? Well, this is in distribution in the space of bounded functions. Okay, or maybe on R, if you like. Okay, and where we define in words, and we will give a few more details now in a sec. This GF is so-called an F Brownian bridge. I'm sorry. Yep, okay. F Brownian bridge. Yep. Okay. So this is the statement, so that, let me make the remark so that the statement, makes sense. So remarks. The first one is going to be, what is this convergence in distribution? Yeah, so that we can understand the left and the right-hand side. Well, convergence in distribution, so far we've seen it in one dimension or maybe multiple, in dimension, but we haven't really seen it for abstract spaces. Yeah, so let me just state what the definition is. So for, general random variables, okay, xn converges in distribution to x, we say so, if we have that the expectation of h is on the sum PR, so h of xn converges to the expectation and this PR, so that again the measure is fixed as the beginning, as in the beginning, and this converges to h of x. Yeah, okay. So this has to happen for all h that is continuous and bounded on this calligraphic space H, which is where the x's live. Yeah? So if you like, general random variables belonging to this calligraphic X or something, or taking values there, I mean. So again, this is, real valued, continuous and bounded functions. Yeah? Okay, so we have this definition, and so what do we, let me just say a few words. Okay, so therefore, what we have is that we are understanding, this difference, rescale difference, as a random variable directly. Yeah. So where would it live? Well, these are CDFs, and it's the difference of CDFs. So yeah, so actually that would live in, some space of bounded functions, for instance, right? So what we do is precisely to view this as random variable taking values in such space, and then and then we apply this definition essentially. So you want to look at the image through any H, yeah, that is continuous and bounded on this space. Now, okay, so therefore for a uniform central limit theorem, we view the left-hand side, and also, by the way, I mean, of course, the right-hand side, but we haven't really spoken about what the right-hand side means, but we view it as a random variable on a functional space, calligraphic X, such as So such as these bounded functions that I was talking about, or CATLAG. Okay, so CATLAG stands for continues to the right, limits to the left in French. Yeah, so these are the initials, or the like an acronym. Yeah. Okay, so and of course it is CATLAG. Yeah, and this difference is CATLAG because each distribution is CATLAG. Yeah. Okay, so okay, so actually the delicate point here, after viewing this as that, so delicate is that delicate point. Okay, so delicate point. Let's say is measurability. Okay, of in this case of such. Well, yeah. Let me just say measurability because I mean, of course, you need. So I was going to say of such random variables, but to be a random variable, you need to be a measurable mapping already. Yeah. Okay. So why did I mention this about measurability? Because most of you, well, not most of you, but some of you may not be doing probability measure, and so then I'm not really requiring you to understand what is going on. But I do want to point it out because it is a key difficulty to deal with, and this has really sparked a tremendous amount of literature in especially in the mid 20th century. So the fact that we have so many sort of authors here actually comes from these measurability issues here. So Doob was the first to talk about this theorem. He didn't really prove it properly. And then Donsker really tried to give the first proof, but he missed his measurability issue. And Skorohod, what he did is to come up with the right topology so that this could be proved. And this was in the space of CATLAG functions, so sort of embedding it with the appropriate topology, which is the Skorohod topology. And then it was quite complicated. So by now, by the way, it's sort of outdated approach, and Dudley came and said, well, actually, let me change this measurability sort of or the sigma algebra that you need to be considering. And he also got another proof, but again, this one is sort of outdated, and generally what one does is actually to relax the definition of convergence in distribution to what is called outer expectations, on this left hand side. But certainly, there is no need for you to know any of this. But I just want to say that so this I forget now, but this Doob sort of started it in the 40s, I believe. Could have been 30s, but I think 40s, and then Dudley could have been 70s or so. Yeah, so this is a good amount of a few decades of literature coming out of from this kind of result. So that's all I wanted to mention about this. Okay, so just by the way to emphasize this, the fact that the left hand side should live in the space of bounded functions or CATLAG functions. Let's try to draw, or visualize what we are talking about. So we have, just imagine that we have a CDF like this, that's from capital F. And then we observe some data from the capital F, and then we construct the Fn. So the Fn, is going to be like a stepwise function, like this, okay, and so on. So that's Fn. Okay. And so if we take now the difference and rescale by n, then what we're going to have is something like, I don't know. So it would be something like this. Okay. And so, this is still living in this bounded space, and let me just say this is square root of fn minus f, and of course it doesn't necessarily correspond to the left-hand side. I was just making it up. Right, but this is just for you to visualize it, yeah? So we'll now specify a bit better what is going on here, yeah? So let me talk about the right-hand side. So this is part of the remark as the second part. So this GF is a Gaussian process, okay? Okay. And so loosely, this means that it is a Gaussian random variable taking values in a functional space. Yeah? Okay. And by the way, it is determined by the same quantities that we would expect determined or characterized, never mind. So the same quantities that we would expect from the finite dimensional setting, and so this is just the expectation of the process. So in this case, it's going to be 0 everywhere, and the other thing is the covariance matrix, or well, in this case there is no matrix, but there is an operator or covariance structure. Yeah. Okay, so the covariance structure, it looks like this. So we have this GF, that S and T, and this is going to be given by F at the minimum between S and T minus Fs Ft. Okay, this is for all S and T in R. So yeah, so let me make a remark, well, maybe a few about this. So okay, so we get this, essentially as you get more and more data, what will happen is that the jumps, that we see here are going to be, smaller and smaller, and so the difference here are going to be smaller and smaller, and then it will eventually converge to some sort of continuous, in this case, Gaussian process. Okay, and of course the Gaussian process should be somehow characterized, or determined by this capital F. Yeah? The way this is being wiggly, of course, should depend on how this capital F, the one we have here, sort of behaves. Yeah. Okay. So, but let me say more importantly that we can generalize. So can generalize the Cramer-Rao lower bound. Okay, for this setting of infinite dimensions, and this GF is going to be optimal. And this is when nothing is assumed. Okay, so this really is when nothing is assumed on the distribution. If we assume some things, then this, this may change. Whether it achieves the Cramer-Rao or not. So okay, so in other words, this Fn is optimal. Yeah? Well, or it achieves it. Okay, so that's good. That's good, because it is telling us that, this very simple idea actually is the best idea, at least when we have no info about the distribution. Okay. So as I was saying, let's get a bit more intuition. So in an important case, is when this capital F is actually a uniform, or the distribution or CDF of a uniform 0, 1 random variable. Okay, so this is what is called, by the way, standard Brownian motion, and we're going to denote it by just simply this G. Yeah, so we sort of drop the F in the F, capital F subscript. Okay, so of course in this case what we get is that the covariance between the two guys. Okay, so this is going to be S minimum T minus S times T. Yeah. And so what you can check here is that, we try to plot this guy, then we're going to get something that is actually tied down at 0 and at 1. Yeah. So it will be wiggly like this. Okay. It will connect 0 and 1 in this way. Yeah. Okay. So tied down at 0 and 1. Okay, so this would be the limit, of something like this when the capital F is a uniform distribution. Yeah. Okay. So there is a theorem, another famous theorem for the capital F that we can talk about now that we've defined this standard Brownian bridge. Excuse me. What did I write? Standard Brownian. No, not motion. Bridge. Yeah. Sorry. Okay. So bridge. So this is what's called the Kolmogorov-Smirnov theorem. Okay, and it says the following. So it says that for any F, capital F continuous, and this is important that it is continuous, the L infinity norm is actually going to be independent of the capital F. Okay, so that's like some magic here going on. And one can also show that, square root of n of now the norm of the difference, and this is in L infinity norm, will converge in distribution to what would generally be the GF, but because of the above, then this is going to converge to the G, or to the L infinity norm of the G. Yeah. Okay. So a remark. So what is really key about this result is that the right-hand side is independent of capital F. Yeah? So that's really, really important. So the independence of the right-hand side on F, okay, so is of key importance. Okay, key importance in applications. Okay, so let's see a couple of examples. So let's take non-parametric hypothesis testing. Okay, so we're going to test H naught being the F being equal to F naught versus the alternative, in which we're simply going to say, well, that F is distinct from this F naught that we have in mind, maybe. Yeah. Okay, so then want to test this, compute. Okay. So compute this guy, just the usual thing, with a naught now rather than F. And we're going to compare it to what should be the true distribution, which is, this guy here. So compare it to the quantiles of this guy that I was talking about. Okay. And by the way, this will have, so this will, this test has versus arbitrary alternatives. So I'll let you think about this, but I remind you that we have two types of tests, type 1 and type 2, and the type 1 is the one that we set, and the type 2 is the one, when the alternative is true, what is the probability of not saying that it is true, so saying that it is negative, and the power is 1 minus that type 2 error. Yeah? So we want to optimize that essentially all the time, and this will have optimal power for arbitrary alternatives. So I let you think that, and then talk about confidence bands. So confidence bands for capital F. Okay, so we can use the quantiles of the guy under consideration, so this guy, to construct uniform confidence bands. Okay. That we're going to note as Cn, and this is essentially a collection of confidence intervals. Okay, so this is a collection of confidence intervals. Okay, and this is for F, of course, such that, and this is important, the probability of this guy belonging to Cx for all x in the real numbers converges to 1 minus alpha. Right? Okay, so how does this look like? Well, if we had our picture from before, so what we're going to have is a confidence band around this Fn. Okay, for the F, so let's plot this. So if we have our F here, and then the Fn doing something like this, not that. Okay. Well, then it will turn out that we can compute, quantity from here, or a quantile in this case, and just add and subtract, whatever we got, and here the same, and then, the probability of this band containing the true distribution should be, set through this alpha. Yeah. Okay. So far we've concentrated, let's say have concentrated on capital F, but it's not necessarily the quantity the one sort of always looks at in non-parametric statistics, so we can do many more things than this. So let's say that we have concentrated on this, but there are many more topics of interest. Yeah? Okay, and so let me give you a couple of examples. So one would be, non-parametric density estimation. This is something that you should guess what it is about. Okay, but also what is called, non-parametric regression. Yeah. So in case you haven't seen it, let me just state it very briefly. And so this is going to be the objective is to sort of concerns finding f, okay, such that for all yi equals fxi plus epsilon I, and this is for I going from 1 to n, and we're going to take for instance, right? So for instance, we're going to take the xi's to be in 0, 1. They could be, somewhere else. And also the epsilon i's to be iid according to normal distribution with 0 mean and variance 1, so standard normal. Right? Okay. So something common to these two problems that we just mentioned, so the density of non-parametric density estimation and non-parametric regression, is the following. So let's see. So in these two problems, the complexity of the models, so we've spoken about this in decision theory. So the complexity of the model is, at least numerically, it is given by or let's say such that it is given by the infimum over the delta n and the supremum over all of the possible f's, but we're not taking small f, but rather large f. Okay, and we're going to look at the expectation under this f of the delta nx minus fx. Okay. And so it turns out this is much larger, generally speaking, than, and under assumptions, of course, than the 1 over square root of n. Okay, so when I say much larger, I really mean it in a rate sense. Yeah. So by this I say the minimax rate depends. I mean, just I think about it, or you must have already, but it depends heavily, and in this case, let's give an example, on the regularity of the functional space, yeah? Or the regularity of the f's. Okay, let's say. Okay. Okay, so and this makes sense, right? Because if we're taking the supremum over a very large set, then of course the supremum is going to be pretty bad. Yeah? That's what we would expect. And so what is surprising, actually, is Donsker's theorem. Yeah? Okay, because in this one we had considered actually, so by the way, when I say regularity on this f, I mean regularity, like if you've seen it, like Helder continuity or Sobolev or Bezov continuity, and so we want the unknown to be contained in a ball, say, for instance, of these sets. Now, of this space. Now, what is really surprising, I think, is that the CDF, you can have a statement in the Glivenko-Cantelli in which it says that it will converge at the square root of n. Yeah? So that's the best you can have, and actually we have a seemingly larger model because we assume nothing about the distribution. So this is really for all distributions. Yeah? Now, the thing there is that distributions are actually very particular. So just as we showed lemma 2, because because there is a lot of structure in distributions, then here is the same story. So the distributions already live in a cat-lag, in space cat-lag, yeah? And they have many other properties, or at least enough so that actually it turns out that they are easier to estimate than the densities, say, for instance. Yeah? Okay, so let's just remark then. So entirely new techniques will be needed for this analysis. Yeah? Required. And so see the example sheet. Okay, and we are essentially done with the course. So I really, I have enjoyed a lot teaching this course, even though it hasn't been, very simple, sort of administratively, let's say, or logistically. That's a better word. Yeah, I think it's a really good course. So I hope you have enjoyed it. And I hope to maybe see you, next term or in part 3. And I wish you the very best in this very particular year. So, right. So see you soon then. Bye-bye.